All right, let's get started. Hope you had a nice spring break. It was relaxing and all that. Um, just a couple, oh, well, I guess you probably need to see, huh? Screen got switched off there. Give it just a moment. Anybody go really far away for spring break, like outside of the country? Me neither. Yeah. I went to Hocking Hills State Park. Anybody heard of that before? It's not far away. It's about 2 hours from here in Ohio. It's got all these waterfalls and rock formations. It's really gorgeous. It's sensational. If you're kind of a outdoorsy type person, you like easy hikes, check out Hocking Hills State Park. Highly recommended. All right, so I've changed the submission deadline for homework 10 to be 11:59 p.m. As you know, usually assignments are due at 1 o'clock, so before class on the day that the due date. But for that one in particular, I just wanted to give you a little bit of additional time in case there are questions that come up in class on Wednesday. So that'll give me the flexibility to address anything that might come up then. The remaining assignments, unless otherwise noted, will continue to be due at the class time as the submission deadline. So speaking of which, a week from today, your submission for part 1 of the research project is due. And I would encourage you to read the full assignment details for that, but the Cliff Notes version is that it should be a 3-page summary of your topic, so like the current situation of that topic, because it's going to be in part 2 focusing on the future direction, or like what sorts of issues are being researched for new developments. And so the current state of the art is what you'll address in part 1. And so the handout has some specific instructions related to line spacing, font size, and all that. So please be sure to review that before you submit your 3-page summary. And the 3 pages is the written portion. And so, if you prefer to have a title page, that doesn't count as one of your pages. The reference list isn't part of the pages. It's 3 pages of writing. All right, and then we're going to go on another treatment plant tour. We've described, I've told you about this before, but that'll be coming up next week, next Wednesday. So any questions about the announcements? All right. So we're going to continue our discussion of wastewater treatment. That's where we left off before spring break. We were just getting into the early stages of talking about pre-treatment. So we'll continue talking about pre-treatment. We'll discuss preliminary treatment and then get into primary treatment. That's 3 different P's: pre, preliminary, and primary. And that's just the sort of thing that I'd love to ask you about on a quiz or an exam is, tell me the difference between those. So we'll get into that today. You may remember that when we were visiting the treatment plant, they talked about how avoiding industrial discharges is a pretty high priority for them in Huntington, where they work with some of the industrial connections and try and prevent toxic chemicals from getting into the treatment plant for two big reasons. They don't want toxic chemicals getting into the treatment plant. One is that those toxic chemicals will generally be bad for the microorganisms that they're cultivating in the treatment plant, and it's the microorganisms that are breaking down BOD. So it kills their colony. That's one of the reasons they don't want toxic materials getting to the treatment plant. And then the other is that their treatment plant's not set up to remove those toxic materials, and so they generally will just pass right through and get into the river. So it's bad for 2 separate reasons. And so a list of some of those priority pollutants that the EPA closely regulates includes things like arsenic, chloroform, lead. You've probably heard of all of those before. Arsenic's a naturally occurring element that's also poisonous to humans. Chloroform was used as an anesthetic. It caused people to go unconscious. It was an early form of anesthesia. Lead, of course, is an element that's a heavy metal, which is toxic to people. It causes brain issues. It causes developmental issues, and it has toxicity. Dieldrin is a pesticide which has some negative health consequences. And then toxaphene, hexachlorobenzene, those are just organic constituents that are used in things like transformer insulation. They're components of solvents that are like paint removers and furniture finishing agents. And so they're just really, there are aquatic species like fish and frogs that are especially sensitive to these materials, and so they try and prevent them from getting into the sewer to begin with. Now, the treatment plant isn't going to remove priority pollutants very effectively, and so the strategy is just prevention. The treatment plant is very good at removing conventional pollutants like BOD, suspended solids, oil and grease. And we can even adjust the pH. We talked about that during water treatment, how the pH can be adjusted with things like soda or lime. And then non-conventional pollutants can be adjusted in wastewater treatment, but it's kind of a rare thing when we're focusing specifically on the removal of these. The exception being nutrients. Nutrients is becoming more commonly removed by wastewater treatment plants, but things like fluoride wouldn't typically be addressed at a wastewater treatment plant. Things like chromium would be very difficult to remove at a wastewater treatment plant. But there's a differentiation between what's considered conventional pollutants and non-conventional pollutants. So regulations is just a really important tool in preventing those toxic pollutants from coming in and harming our bacteria in the treatment plant, and then getting through the treatment plant and harming the aquatic species that live in waters downstream. And also, we consume the river water, and so if dieldrin or chromium gets into the Ohio River, then that's going to affect the next community downstream. So the corrosive chemicals are bad for the environment. They're bad for oftentimes the materials in the treatment plant. They can be corrosive to pipes. They can cause damage to pumps, and so we just prefer to get them out there. And so the EPA has legislative authority that allows it to regulate industrial discharges that are thought to be harmful. And rather than regulating them one by name, in having an ever-growing list of things that you're not allowed to put into a treatment plant, they generally regulate them by categories instead. And so here's a list of categories of things which are limited in industrial discharges, like both gasoline and diesel fuel can't be discharged to a sanitary sewer because they are capable of causing a fire or an explosion. But that would also extend to things like HMX, which is an explosive, or TNT. There isn't a long list of things that would cause fire explosion. It's just sort of taken as a given that if you're in the business of producing those chemicals, that you'd be aware of the risk of putting it into a sewer. And so this is just a list of things which, because of the effect, would be prevented from discharge to a collection system. So if you look at some of these things, obviously solid or viscous pollutants that would obstruct flow. So even though gelatin wouldn't necessarily be toxic, it wouldn't be dangerous from a human health standpoint, it's not dangerous from the standpoint of even interfering with the treatment plant necessarily, but a heavy gelatin or just flour, putting flour into the sewer could congeal, could block the flow, and could limit the capacity of the pipes. And so that's kind of the sort of thinking of each one of these rows, is just that there is some negative side effect that we're trying to prevent by limiting discharges, and that's why the EPA regulates them. So it's partly about putting laws in place and working with big-time polluters and likely culprits for industrial discharges, but it's also about public awareness. And there's a growing sense that just making people aware of the fact that stormwater and wastewater go to the river is going to help people to be more careful about the sorts of things that they pour down the drain. And some communities that are generally on a river or in a coastal area, they'll have like a spray painted little blue fish next to the storm drains to give you the idea that, oh, you shouldn't probably pour your antifreeze down the storm drain because it's going to the river. So they just try and reinforce the awareness that these discharges are going back to the environment. So you can see here an advertisement that's talking about how it's bad to put grease down your drain. And not only is it bad for the plumbing in your house, but it's also bad for the plumbing that's owned by the wastewater treatment network, owned by the community. So pre-treatment is not actually treatment. It's just policies and educational programs that try and bring awareness to the need to avoid putting things down the drain. Pre-treatment can also include inspection of restaurants that have a lot of grease and maybe, so think about a place that's making French fries or is cooking lots and lots of hamburgers. The quantity of grease that they generate is such that they'll often contract with a special hauling company that will come in and take the grease. And they actually usually lock those dumpsters up pretty tightly because grease has become valuable as a fuel where it can be filtered and blended and mixed with diesel. You maybe heard of biodiesel before, and there are places like in Northern California where biodiesel, well, the bio component of biodiesel is a really significant fraction of the fuel. And so they'll take grease, filter it, and then they will sometimes have to go through a chemical reaction to precipitate out some of the heavy chains that would cause the liquid to be too solid at low temperatures. There are a handful of cars that have been modified to run directly on vegetable oil without any further treatment. They have to heat up the fuel before it goes to the engine. But grease is it's a resource. In fact, most of our waste have in some way the capability of being considered a resource. If we're able to extract the phosphorus and nitrogen from wastewater, then those could be used as fertilizers. If we're able to apply the organic material from wastewater onto the land, then that can be a fertilizer as well. The organic material can help to improve the quality of soil potentially if it's not containing heavy metals and so on. So this is just another illustration of how if you are bringing awareness to the need to keep grease and oil out of the wastewater treatment plant, then maybe people are going to be more prone to recycling it and trying to find a helpful application for it. Of course, there are some people who aren't connected to the sewer at all. They have a septic tank at home. I've got a septic tank. How many of you have septic rather than being connected? Maybe some people don't even know in a lot of cases. But if you live in a rural area, chances are good that you've got a septic tank rather than being connected to a pipe network, because it's not economically viable sometimes to put in a pipe when houses are really spaced far apart. And I live in a place where most of the houses in the area have 2 acres, maybe up to 30 or 40 acres in some cases. And it's expensive to put a pipe in the ground. And if they're only going to be getting $20 a month from me, then it doesn't justify the expense of a concrete pipe all the way from wherever it left off to my house. So instead, I've got a septic system. And the way it works is, you can see here, there's both a top view and a side view. But when you flush the toilet, water goes to a concrete vault that has generally 2 different sides to it. And in the first part of the vault, the purpose is to allow the solids that will settle to go to the bottom of the tank. Grease and oil will float to the top. And then you draw off the water from the middle. And you send that to what's called a leach field, or sometimes it's called a tile drain. And what you're essentially doing is you're taking the water and you're just injecting it into the soil. And the concentration of BOD is pretty high in this wastewater. You're removing some BOD by having the physical separation of the solids, but the water that comes out of a septic tank may have as much as 100 to 200 milligrams per liter of BOD. And we put it into the soil in the hopes that the bacteria that live in the soil will break down the BOD. They'll neutralize any pathogenic bacteria. So the bacteria that live in the soil generally don't make us sick because they're consuming food that's different from what they'd find in us. Soil bacteria and the bacteria that are pathogenic to humans, they don't generally overlap. So it's not a good environment. The bacteria that, like E. coli or viruses that come out of us, when we put them into the soil's too cold, so they don't survive for very long. And there isn't the food that they need to continue living for a long time. So it's relatively safe as long as we put this septic tank effluent into areas that are separated from the groundwater table. Like if the water table's high and we're trying to put our liquid waste into that, then the liquid waste may come to the surface, or it could get into a creek. And sometimes you can even smell it. If you're in a rural area and you're walking alongside the road, you can sometimes smell when people's septic tank is actually not, if the wastewater's not staying in the soil. So every city has different regulations on how deep you have to go with the leach field and what the separation with the water table should be. And some places have regulations that you need to add aerators to your septic tank if the water table depth is relatively close. But the bottom line is that you're operating your own wastewater treatment, and then every few years you'd have to pump the sludge out of the bottom of the tank. There are some places, like homes, where they only have needed to remove it every 20 years. If you have good biological activity, if their bacteria that are growing in a septic tank will break down the sludge. But of course, the things like paper and grit, those aren't going to break down from bacteria, so that will accumulate at the bottom of the tank eventually. So this is just a little side tangent, the acknowledgement that not everybody uses a sanitary sewer, and septic tanks can be an effective way of treating waste in remote locations. Okay, now back to the treatment plant. We talked about pre-treatment. Pre-treatment is public education campaigns and regulations to try and keep things out of the sewer. Preliminary treatment actually begins at the treatment plant itself, whereas pre-treatment is it's at the source. It's talking about at the restaurant, at the industrial facility, in people's homes, just trying to prevent them putting things into the sewer that they shouldn't. Preliminary treatment is the first step at the treatment plant itself, and it includes things like grinders, which try and break down debris so that it can pass through the treatment process without causing damage. Bar racks, which we saw a bar rack when we were visiting the treatment plant here in Huntington. We saw a grit chamber, and some places may have flow equalization basins as well, and we'll talk about each one of these. These preliminary treatment operations aren't going to remove suspended solids and BOD. It's more about conditioning the flow so that the things that we do after preliminary treatment operate more effectively. So we're removing debris that would cause problems, or we're trying to stabilize the flow rate so that it's not like a big surge of flow during the day and really low flow rates at night. That's the purpose of flow equalization. Trying to move grit that would cause damage to pumps and to the pipes because they're abrasive. So the purpose of preliminary treatment is conditioning the flow, but not the removal of BOD or suspended solids. All right, here's a grinder. I want to show you a video. Unfortunately, it's not the best quality video, but it will give you the idea of what a grinder does. All right. called the Muffin Monster. Kind of a weird name, but I'll pause this. That is to grind stuff up that otherwise would cause like a clogged pipe, or maybe would damage a pump. So when we were visiting the treatment plant, there was a shoe insole floating around in one of the aeration basins, and if they had run that through a grinder, then it presumably would be able to settle or float more easily. So if something is like more dense than water, then it would sink, and if it's less dense than water, it's going to float. But the scrapers that are in the clarifiers would be able to like move the material more easily the smaller the debris is. And so that's the purpose of a grinder. Sometimes those are also called comminutors, and oftentimes those would be installed downstream of a grit chamber. Sometimes they're used instead of having a bar rack. Sometimes they'll have both a bar rack and a grinder, but now you know what a grinder is. A bar rack is, we saw that there was a bar rack, but we didn't actually see how it was operating when we visited the treatment plant. So let me show you an illustration of that. Okay, so you can see that water would be flowing through this screen, and it's going to have garbage in it, but there is kind of like a squeegee that pushes the debris up over the screens, and then at the top is an opening where the debris would just fall through a chute and go to a dumpster. So if you didn't have that system to occasionally clean the screen, then it's going to become clogged with the debris, and water couldn't flow through it effectively anymore. So it looks like this is probably a 1/4 inch, which is what they're going to be putting in at the Huntington treatment plant. They've got a 1-inch screen, but they're switching it to a 1/4 inch. So that's going to get out some of these things that, it's just trash that's going to interfere with the flow downstream if we leave it in. All right. So the materials that are gathered have to be landfilled, and as much as possible, you'd like to have very little organic material accumulated. So you want the human waste to go through, but you want the solid materials to not go through. And so that's why they can't get like too fine in the screen, because then eventually the solid waste would accumulate on the bar rack, and we don't want to send that to the landfill. So there's kind of like a Goldilocks zone of having a mesh that's fine enough that it's going to trap the debris that would cause damage to the treatment plant, but it's not so fine that it's trapping solid waste. Okay, so grit removal is an important step of pre-treatment, because the sand and gravel and broken glass, if it remains in the water, then it's going to ruin the pumps very quickly. The impellers that are moving very fast are sensitive to the abrasive grit that can be present in wastewater, and especially when we have a combined sewer in Huntington, you're getting a lot of stuff off of the road. So you may be wondering, like, where is the grit coming from? Are people like flushing sand down the toilet? And it's not that. It's that the material like asphalt from the road is breaking down over time, and people put sand on the road during icy conditions, and when that melts and gets into a combined sewer, then it flows along with the wastewater towards the treatment plant. So the two main ways that grit is removed is either with an aerated grit chamber, which is what they have in Huntington, where they're using an air diffuser to cause kind of a helical trajectory of the water as it goes through. So you can see that the rising air bubbles are going to cause a circular motion of the water, and let me show you. Oh, there's the statistic of there's between 30 and 90 cubic meters of grit per million cubic meters of wastewater. So it's a tiny fraction of the overall volume of wastewater, a very small fraction of the wastewater, but has the potential to cause a lot of damage all the same. So this is showing with a little bit more detail the trajectory of the water. It's both circulating vertically and also horizontally as the water goes through there. An advantage of that is that it causes the grit particles to reach against the side of the wall and then settle down the wall and to the center trough. And by keeping the water aerated, then that's a good way of preventing organic waste from settling at the bottom of the grit chamber, because later on we're going to have a primary clarifier as a part of the primary treatment where we do want solid waste to settle. But we don't want the solid waste and the grit to settle in the same place because we're doing different things with them. The grit is going to be landfilled along with the stuff that comes out of the bar screen. The grit, we're going to maybe just rinse it off but then send it to a landfill in a truck. But the solid waste that settles in the primary clarifier, we're going to either digest it or recirculate it or dry it before it's sent to the landfill. So we need to collect the grit separately from organic waste, and the aerated grit chamber is really good about that. It provides enough movement in the chamber where the grit is relatively dense. You know, it has a density of 2.5, 2.6 grams per cubic centimeter, and so it'll settle a lot faster than solid waste will, which has a density which is closer to 1 gram per cubic centimeter. So grit chambers are usually pretty small. You only need the water to stay in there for a couple of minutes for the grit to settle out. They would generally have a depth of between 2 to 5 meters, and they're oftentimes kind of rectangular in shape, where they're longer than they are wide, so that as the water flows through it, it's a little bit like a plug flow assembly. Despite the mixture, the water's still passing through in a direction rather than just it being a square settling tank that doesn't have any directionality associated with it. The other type of grit chamber is a horizontal flow grit chamber where it's not aerated. It's not trying to push the grit around with aeration, where it's just really a wide section in the pipe where the flow velocity settles down and it settles low enough that the grit can settle, but hopefully not so low that the organic material will settle. And then they'd have like a mechanical assembly to sweep the bottom of the grit chamber and then remove the accumulated grit with some sort of like it could be a screw conveyor, which is a positive displacement pump. And either way, whether we're talking about a aerated grit chamber or a velocity controlled grit chamber, here's the formula that describes the settling velocity of grit particles. It's Stokes' law. Let me give you an in-class exercise that, because we're having to cover kind of a little bit more ground than usual to make up for the time that we spent at the treatment plant, we're going to go through 2 in-class exercises today. And I just wanted to cut straight to the chase and give you the solution. So, Stokes' law assumes, I think we've talked about it briefly before. It assumes a spherical shape for the particles that are settling. And so in the sizing of a grit chamber, you'd need to know the flow rate of the wastewater, because if you're sending wastewater through a grit chamber of a certain size, that's going to determine how long it spends in the grit chamber and what the horizontal velocity is through the grit chamber. Because we'll have a particle that's settling down, and we want to make sure that we provide enough time in the grit chamber for the particle to settle downward. And so we would need to know like the intended width of the grit chamber, the flow rate that the water is going through, and then therefore the horizontal flow velocity, and then a little bit about the particle characteristics like the viscosity of the particle, the viscosity of the water, the density of the particle. So in the handout that I've given you, let me just pull up the solution so I can bring it up on the screen. It takes you through the process of, first of all, calculating what's the settling velocity of a certain size grit particle. So let's say that we know our pump won't be damaged by particles that are smaller than 0.15 millimeters, but everything bigger than that does need to be removed. So that's our critical particle diameter that we're using for the grit. So you can see I've converted that into meters. And then we can find the settling velocity for a particle that is sand and has the typical density of sand, 2650 kilograms per cubic meter. And so the difference in the sand density and the water density is one of the driving factors in how quickly it settles, as is the diameter of the particle and the viscosity of the fluid. So this particular particle is going to settle downward at a rate of 0.02 meters per second. So that's how fast it falls down. And so what we do now is we'd find out like how tall is the grit chamber going to be. If we know it's going to be 0.75 meters wide and we're looking for a flow velocity of 0.3 meters per second, then we use this continuity relationship of flow rate is velocity times area to find out what cross-sectional area and therefore what fall distance, what depth, how deep the water is going to be in the grit chamber. So if it's falling a distance of 0.444 meters and it's falling downward at a velocity of 0.0202 meters per second, then it's going to fall for 22 seconds. And then if we know that it's proceeding through the settling chamber at a rate of 0.3 meters per second, that tells us how long it would need to be in order to have that critical particle, assuming the worst case scenario that it starts at the very top of the grit chamber and has to settle down through the entire depth of the grit chamber column, then 6.6 meters would be sufficiently long to capture that critical particle. So any particle that's bigger than that is going to settle faster. And some of the particles won't start at the very top of the grit chamber, so they don't have as far to fall. So this is similar to some of the settling calculations that we did in water treatment as well. Stokes' law is what we can use. And so that's how to do it for a grit chamber. Does anybody have any questions before we move on from this illustration? Okay, so flow equalization is the other thing we're going to talk about today, and it's included on the homework, by the way. I think there's a grit chamber problem on the homework, and so now you've got a handout that kind of illustrates those calculations. I'm also going to give you a handout that illustrates how to do flow equalization basin calculations. Now, not every facility has a flow equalization basin. The advantage of having it is that it smooths out the flow so that you're not in the middle of the night having hardly any water going through the treatment plant and then during the day having a huge deluge. Because people generally sleep at night and generally don't use a lot of water when they're asleep. That means that there's very little water coming to the treatment plant at night compared to the daily average. So this dashed line is just showing for a daily average, there's a certain period when the flow rate coming into the treatment plant is low, and there's another part of the day when the amount of water coming to the treatment plant is much higher than the average. So if we put in a tank to try and smooth out those daily variations, then that's going to improve the performance of the treatment plant. It's going to improve the biological removal of BOD because the bugs don't want to be starved at night and then overfed during the middle of the day. Microorganisms, they remove BOD more effectively if they're fed at a constant rate of BOD. So putting in a flow equalization tank kind of acts as a shock absorber in a sense. And it will help to cushion and smooth out the peak flow and the low flow. So to do a flow equalization calculation, what you'd first of all need to know is, over time, what does it look like in terms of the flow rate in and the concentration of the waste over time? And you may be wondering, like, why would the BOD change during the day? And that's because what flow does make it to the treatment plant at night is largely related to infiltration and inflow, which we've talked about before. That could be like groundwater getting into the pipe through a crack in the collection network. And groundwater doesn't have BOD. Water from people's roof drains or foundation drains doesn't have BOD. So typically, the low flow rate time in the middle of the night is also a time when there's a lower concentration of BOD. And then you can expect the concentration of BOD to be higher during the day when humans are contributing waste to the collection network, to the sewer. So the flow equalization basin is going to dampen both of those, the flow variation, and also going to dampen the variation in the BOD concentration. So what we need to do is analyze when is it during the day that we would see the tank begin to fill. Because at night, if you think about, there's a big tank full of waste that we stored during the previous day. So like the extra wastewater that's coming in over and above the average daily flow is collected in the afternoon and the evening. And then at night, during the low flow rate times, what we're doing is we're kind of drawing the water out of the storage tank, and then that's what we're going to be treating in the middle of the night. We're treating the water that had been stored earlier in the day. So the first question we need to ask is, like, when during the day is the incoming flow rate greater than the average daily flow? So this is best done on a spreadsheet. I'm going to give you the handout here, and then we're going to open up a spreadsheet file that illustrates how to do the calculations. And on the back side of here is the solution. Okay, so you've got a homework assignment that's pretty similar to this. And so you'll be given time, flow rate, and concentration. By the way, did everybody get a copy? Okay, good. So just translate that, put in the same data, the time, flow rate, and concentration into Excel. And the flow rate in varies over time, but the flow rate that you're taking out of the tank is constant. And for it to work out, for the daily cycle to meet, you want the total volume in to be equal to the total volume that you take out in a 24-hour cycle. So we're just wanting to calculate what is the average flow rate in during the day, and then that's the same flow rate that we're drawing out constantly. And so you can see here I've just typed in the flow rate in and the concentration in. So I took the average of the 24 hours worth of data, and so the flow rate out is going to be 0.2704 cubic meters per second. So that's the answer to part A of this one, where it's asking, determine the average daily flow. This is the flow out from the basin. The average daily flow is just the average of each of these different hours. And the data is provided in 1 hour increments, so we can do the simple average to find the average daily flow. Okay, so now if the average daily flow is 0.27, now we need to find out when in the morning is the first time that the basin will begin to fill. So remember, through the night, the flow rate coming in is less than the average, and so we are using the stored waste from the previous day to feed the treatment plant overnight. And then there's a certain hour of the day when the flow rate exceeds the average. And so through the night, you can see the flow rate in is less than the average, still less than the average. And now at 11 a.m., the flow in is 0.28 and the flow out is 0.27. So this 11 a.m. represents the time when we've used up all of the water that had been stored in the previous cycle, and we're just starting to fill the tank now. So 11 a.m. is when we begin to fill the flow equalization basin, since flow in is bigger than flow out of the tank. So that's at 11 a.m. So I'm going to reorganize this data. This says part C, reorganize the list so this time that you identified is the top of the list and then it continues consecutively. So here on the back side of the paper is what you're seeing, the result of this, where we've got the 11 a.m. at the top of the list. So here's the flow rate in and the concentration. So this is just all given data. Column A, B, and C is just given data, but I've reorganized it so that the daily cycle starts at 11 a.m. So it goes 11 a.m., noon, 1, and so on and so forth through the full daily cycle, but then I don't repeat 11 a.m. at the bottom of the list. The last hour is the 10 o'clock hour. So 10 a.m. is at the bottom of the list, and if we counted this, it's 24 hours. So the count, there's 24 hours of data. And the average is the same. The average is still 0.2704. That's the average daily flow, and that's what we assume the flow rate out of the tank is. Okay, so this next process is I've added a few column titles here, and we're going to go through the process of trying to figure out how big does the storage tank need to be, and then also how does the loading of BOD change over time. So column D is the flow rate in multiplied by 3,600 seconds per hour. So column D, this is called volume in during the hour. If this is the flow rate in, volume in is just flow rate times time. So 3,600 seconds in an hour, so we've multiplied, in this case, 0.28 cubic meters per second times 3,600 seconds, and you get the increment during the 1 hour period between 11 a.m. and 12 p.m., how much flow in was there. And we do that for every row, for every hour of the day. So once you type the formula in a single time, obviously you don't have to type that formula over and over. You can just drag it down and it'll apply the formula to each row. Okay, the flow rate out, you're going to just assume that the flow rate out is the average daily flow in. So here, I found the average is 0.27042. My recommendation is rather than keying that in, just reference down here where you calculated the average daily flow. So you can see that I've got it anchored here. I'm referring to the cell location where the average daily flow was. So that's the flow rate out in terms of Q. And then the volume out during the hourly increment is the flow rate times 3,600 seconds. So then the accumulation is the difference between in minus out. So accumulation is in minus out. So there's a little bit of water that is stored in the tank because the 28 cubic meters per 0.28 cubic meters per second is coming in, a little bit less than that's going out. So over a 1 hour time increment, we accumulate 34.5 cubic meters during this hour. And so this is just hour by hour how much is accumulated. And what you'll notice is during the day, there's a positive accumulation. And what's the total amount? Look down here at the sum. 4303 is the sum of the inflow. And then at night, we have outflow. And what is the sum of the outflow? 4303, but negative. So it's in balance. The amount that flows in during the day is the same amount as the volume that flows out at night. The cumulative volume is going to be, for every hour except for the first, it's going to be how much volume was in the tank in the previous hour plus the net accumulation of this hour. So it's like the tank is getting more and more full. And what's the maximum volume of water that's ever in the tank? It's right here before it starts to drain. So here's the max. This is the most water we need to store. And then the liquid level starts going down again, and it drains, and eventually drains to 0 at the end of the cycle. So this accumulation is for every hour. It's the previous hour's volume of how much is in the tank plus either the increase or the decrease associated with that hour. So you'll notice the volume is getting lower with each successive hour here because we've got the previous hour's volume and then a net outflow. Okay, column I is basically looking at the concentration times the volume of water that came in. So this is the number of kilograms of BOD that comes in during an hour. So it's the mass of pollutant that's coming in, which is dissolved in the water. So we divide by 1,000 because BOD was in grams, and we want to express this BOD here in kilograms. So the formula is at the top. You can see which columns I'm doing. So we're just finding the mass of BOD that comes in. And this is probably, column J is the most complicated one. To find the concentration of the BOD in the basin at a given time, we need to look at both the previous hour's concentration and then also how much stuff came in during the hour that we're looking at. So for the first hour, the concentration of BOD in the tank is just the concentration of the waste that came in. But then from there, we're like averaging, and we have to keep track of the previous concentration and how much liquid was in the tank during that previous hour, but then also the effect of the new waste that's coming in. So if you look, the BOD that's coming in varies between 75 and what's the most we get up to, 220? If we have this flow equalization basin, it's acting as kind of a shock absorber. We don't have it go as low as 75. The low only gets down to like 125 approximately, and it doesn't get quite as high either. So it smooths things out. This is the concentration, and then here's the mass flow out of BOD given an hour. So here's graphs that just show the effect of the flow equalization on how the concentration is cushioned over time and how the mass loading is cushioned over time. So you've got this spreadsheet illustration, and hopefully that'll be useful, but I recognize this column J in particular is a little bit complicated. So, you know, if you run into issues as you're working on it, feel free to stop by my office and I'll be happy to help you with your spreadsheet. That's it for today. I'll see you on Wednesday. Remember, your assignment is due by, let's pull this up, 11:59 on Wednesday.